thanks for the introduction, and I thank all the organizers for the opportunity. And I'll be talking about the tensor category, the Virasoro algebra and the quantum groups. And right. And okay, so up to this point, all the lectures and a talk has mentioned the conformal blocks, and there will be no exception about that. And my work, this is jointly with colleague Koshida from Aalto University, and our result is from 2022, so it's quite old in some sense. Except that in our paper, what I say today is not phrased in the way how I say it today. So yeah, so I'm revisiting the new to me language. Okay. So, yeah, so whenever you see the conformal field theory, I think they're from, either from physics or mathematics, or either from probability theory or representation theory. I think we all agree that we encounter primary fields and their operator product expansions. And how to deal with these structures, there are a lot of options. One option is to see that primary fields are simple objects in simple objects, and the operator product expansions are tensor product of these modules in some abelian category. So the easiest, simplest example and the most famous example is the Ising model that consists of primary fields 1 sigma psi, and that satisfy those fusion rules. All right. So there are two very famous sources of this kind of tensor categories. One is quantum groups, and the other is the Baltic operator algebras. So they arise as module categories of these algebraic structures. Of course, a quantum group is a kind of another name for Hopf algebra. So its module category is tensor category. Obviously a tensor category, so let's start with a very easy example. I'm not sure if you have to say anything about the quantum group in front of you, but just for completeness, a quantum group is a Q deformation of enveloping algebra of Lie algebra, and the example that I see is the quantum group of SL2. So that is algebra generated by EFK, subject to those relations. And the category CQ, where I write CQ, is the very famous category of finite dimensional representations of this algebra, on which the operator K, its spectrum has the form of Q to the power of an integer. So that's called its type 1. And it's very famous and it's very old, that result, that when Q is not a root of unity, this category is simple, and simple objects are labeled by positive integers. The labeling is a little bit non-standard in that so that R runs over positive integers, and I say that highest weight is Q to the power of R minus 1. So usually, maybe you label these by lambda, which runs from 0 to infinity. Yeah, thanks. Yeah, but anyway, so that's the labeling. And the quantum group is a Hopf algebra, so the tensor product of two representations is obviously a representation of the same algebra, and it's decomposed into simple object by the Clebsch-Gordan rules. Although this is a very obvious example, it might be worthwhile to ask this question: where is Q dependence? Because this category has exactly the same simple objects as SL2 and exactly the same branching rules as SL2. So it might look like we are not able to distinguish a quantum group from the Lie algebra, which is of course not the case, because when we think about the tensor category, the associativity, which is an isomorphism between one way of iterating a tensor product to the other way of iterating a tensor product. This is a part of the structure of the monoidal tensor structure. So if you compare these two Hopf spaces, this associativity isomorphism naturally induces isomorphism between these two home spaces, and because these two home spaces have natural bases. Right? So on the right-hand side, we first plug in R0 to the tensor product of S and R3, and you insert S into the tensor product of R2 and R1 and R2. This is one base, this is this home space. And on the right hand, we have the similar bases. And if you think about the matrix element of this homomorphism in these spaces, you get quantum 6J symbols, and that depends on the Q. So this is how we measure the Q dependence in categorical way. Right. The other side is vertex operator algebra, which is a complicated algebra, in contrast to that quantum group is just associative algebra. So I have taught a course of vertex operator algebras for a semester. I ended up with very basic of the stuff. It means that vertex operator algebras deserve such a lot of time. But let me try to sketch what it is. So vertex operator algebra is a quadruple of Vy1 omega, and V is a greatest vector space, and Y is a linear operator, linear map from V to the formal series in X with coefficient in and V, and 1 is a distinguished vector, and omega is another distinguished vector, and I require that these two operators have the same specific degree. Actually, I'm thinking that maybe omega living in V2 follows from the axioms, but I'm not sure yet at this point. Maybe the name of those things, the V is of course the space of states, and the Y is called the state field correspondence. The 1, this is vector as this notation suggests, this is the vacuum vector, and omega is omega plays the role for the stress energy tensor. So the axioms of those stuff is there are a lot of axioms, and I don't think I have to go through all of them, but let me make a few comments. For example, one of the vacuum axioms says that if I apply the field corresponding to A to the vacuum vector, it is expanded into the positive power, non-negative powers of X, and you get A itself out of in the constant term, which means that although this is why I say Y is a state field correspondence, Y is certainly an operator that assigns a field to a vector, but you can come back to the vector that inserted into the Y. So you can recover the vector out of the field. So it is rarely a correspondence. And I said omega is the stress energy tensor. To be precise, the field corresponding to omega is the stress energy tensor, because if you expand it in terms of the formal variable, the coefficients should satisfy the relations of the Virasoro algebra. And the last one is, I think, the most important. This is locality. If you think about the commutation relation between the field for A and the field for B, that will be annihilated by multiplying certain very large power of x minus 1. So what this means is that the commutator of these two fields is supported on the locus where x and y coincide. And so in this sense, I would say that the VOA is almost commutative. It might be worthwhile to making this comment, or might not be worthwhile. So let's see. It might be worthwhile because I will see that some similarity between VOAs and commutative algebras, and it might not be worthwhile because the similarity that I will be observing, I'm not sure if that comes from the locality. So anyway, right. Of course, the vertex operator algebra is algebra, so you can think about its modules. actually, module is, of course, if you have an algebraic structure, a module is, of course, the vector space, and you can just push the axioms of the VOA to the modules. That's natural, but unfortunately, the axiom sets that I presented here cannot be pushed to the module. So I have to define the module in a certain way, which I don't want to do. So just let me say that the module over a VOA is a pair of a vector space and a state field correspondence map, but this is not really a correspondence, so this is just a module map, I would call it. But anyway, it is a linear map from V to the formal series of X with coefficient and W. And that satisfies those such and such conditions. The most famous example of the vertex operator algebra is certainly the Virasoro vertex operator algebra. So the Virasoro algebra is a infinite algebra with those relations. And Virasoro VOA is constructed this way. I take a certain number C, which is the central charge, and the VC is the highest weight representation of the Virasoro algebra, so on which the central charge is exactly acting by C. And one point you have to notice is that I'm annihilating L-1 out of in this quotient. This is important because the vacuum must be annihilated by L-1 for the VOA. So this representation of the Virasoro algebra has a unique structure of a VOA by saying that the image of 1 is the vacuum vector and the image of L-2 is the stress energy tensor. And yeah, it's kind of tautological, but the structure of the VOA is determined by saying that the omega corresponds to the stress energy tensor. Right. Yeah, and I call it Virasoro VOA. There is some subtlety between the terminology because this VOA is sometimes called a universal Virasoro VOA, and there is a minimal VOA that happens when C. So this highest weight representation might not be irreducible as the representation of the Virasoro algebra. When it is not, the simple quotient is called the minimal VOA. Otherwise, otherwise this is simple, but yeah, but this is the universal one among the Virasoro VOAs. So what are modules over this Virasoro VOA is actually this vertex operator algebra has a lot of modules, and actually any Virasoro algebra module of central charge, the same central charge, on which for any vector W, if you raise the number n very large, then the result must be 0. So if this condition is satisfied, such a Virasoro module is automatically a module of the universal vertex operator algebra. For example, a Barma module is a Virasoro VC module. So the Barma module was, I take the same number, same central charge C, and I take another complex number H, which is maybe called conformal weight. So it is also a highest weight representation where the highest weight, so on the highest weight vector L0 acts by H. All right. So maybe before going further, I think I want to present a wrong tensor product. So yeah, let's say this is W2. Okay, so there are two modules, W1 and W2, and they are VC modules, so it is a Virasoro representation on which Ln acts locally. I mean, if n goes too large, then it acts as 0. So, by the way, the Virasoro algebra, it's enveloping algebra is a Hopf algebra, so why not why not the tensor product, and you can define the representation of the Virasoro algebra by the Koshida fraction. This is wrong. the answer, the reason is very clear, because if you think about the action of the center, it acts by 2C on the tensor product, and this is not a module of the same Virasoro VOA. What is wrong with this is that we took the tensor product over C, so what we are looking for is the tensor product over the vertex operator algebra. Okay. So that's observation of the wrong tensor product. So the result is like that. So it's very common to parameterize the central charge this way in terms of a complex number T. I think I have to assume that T is non-zero. And there are this table of highest weights called class table. This is exactly where the Varma modules are degenerate. Varma modules are not irreducible. And so let's assume that T is not a rational number, and then I will call the category generated by LR, which is a simple quotient of the Varma module associated to HR1. So we call these modules the first row modules because it lies in the first row of the class table. And the category ET is an additive category generated by those simple objects, these representations. And I can say that if I define the correspondence between the category of UQ SL2 modules to this ET plus by saying that the U are it goes to the LR, then this is a tensor equivalent when we set this parameter matching when Q is exponential of pi I t. So this is where we're going to see. But of course we haven't seen how we can formulate the tensor product of the vertex operator algebra modules. So okay, so there is before that I have some historical remarks. So this kind of duality between quantum groups and vertex operator algebra has a long history of, especially when the vertex operator algebra comes from the finite algebra, and this kind of duality is sometimes called the cardinalistic duality. And even for the Virasoro case, there are lots of works. And in that sense, our work is not really the unique, the only one that addresses the Virasoro VOA. For example, these 5 people papers, they show that the category of what is called C1 cofinite modules over the same vertex operator algebra is actually braided tensor for all T, not only the irrational T. And also, the second paper had determined the tensor structure when the parameter T is taken to be 1 over P, which is thought to be interesting these days because the tensor category is not semi-simple, and the semi-simple categories might be more interesting than the semi-simple. Non-semi-simple category might be more interesting than semi-simple categories. And furthermore, in the same parameter, Gannon-Neglon shows that there is a tensor category generated by L2, and that is equivalent to the module category of UQ SL2 at the root of unity. So yeah, so these are related work. I think despite those related work, I think our approach is worthwhile in that we really compute 2 categories directly. So yeah, let's see how it looks. So before looking at how to define the tensor product for the VOA modules, it might be worthwhile or it might be instructive to see what is the tensor product anyway, except for the vector spaces and the representations of a Hopf algebra. What can admit tensor product is a module of a commutative ring. So R is a commutative ring, and for commutative ring, I can think about the set. I take R modules, and I can think about the set of R multilinear maps from the product of M1 through Mn to N, and then okay. So what is the tensor product over R is M1 tensor, M2 is the representing object of the functor that assigns the set of multilinear maps from R module category to set. By representing, I mean that really the result of applying the functor to a certain R module is the same as the applying N to the home functor, and this is not only isomorphic, but this has to be natural on all N. So this is how we usually, people usually think about the tensor product over an algebra. And if we define tensor product this way, there are two important properties of that. One is the unit law, and the other is associativity. For the unit law, it doesn't matter if you tensor the algebra itself; it comes back M. This is because if one of the module is R itself, it is determined by the value of the element. So there is a natural map between. You can just drop the first element in this set. So, but this means that M itself represents the same functor as our tensor M. So there is a unique isomorphism between them by Yoneda's lemma. For the associativity, the similar things happen. In this case, we think about the three modules and one module. And what we can do is, if you want to think about the linear map from three modules to one module, you can actually glue two of them and replace it by the tensor product over R. And by definition of the tensor product, you go to the home functor of this form, and you can do the same with the last two modules, and you come to the same result, which means that one way of iterating the tensor product and the other way of iterating the tensor product represents the same functor. So there's a natural isomorphism between them. So the observation is that all the definition and the good properties of the tensor product comes from the good properties of the set of multilinear functions. Right. So with the VOA, the same role is played by the space of conformal blocks. Okay. Right. And I call the conformal, the space of a conformal block is the dual of the space of co-invariance that we have seen in the last lecture. So how to define the conformal blocks? The first step is to form a vertex operator algebra bundle. For that, I take a vertex operator algebra and a Riemann surface X. And given that I can form a vector bundle of infinite 1 over X, that looks like as follows. For every point, the fiber of the bundle looks like it consists of pairs of local coordinate at the fixed point and element in the vertex operator algebra. Modulo this relation so that if you change the local coordinate in the left, it affects the element of the vertex operator on the right. And the action looks like this. So any change of local coordinate looks like infinite series in the local coordinate, and if you express the local change of local coordinate by exponentiated vector fields, given this expression, you get an operator by replacing the bit vector field by Virasoro operator. So that's what I have in here. By construction, so I impose this equivalence relation to the fiber. And by construction, every time you fix a local coordinate, the fiber is locally trivialized locally trivialize with the vertex operator VOAB itself.
Sorry, how did you find those, or why do you impose those conditions?
So the point of viewing this is that V is something abstract vector space, whereas curly Vx is somehow the same vector space, but I want to incorporate the effect of choice of local coordinates. But if I just take the product, it's too big. Yeah. I don't know how it's going. This is the abstract algebra, abstract vector space, where this is the actual geometric object.
Well, I guess you want to preserve some sort of structure. That's why you're imposing this, some sort of VOA structure. I think what I want to see is if there's any reason from VOA perspective why you want this.
We are going to see how it happens. I think. Okay. The last thing is this vector bundle is equipped with a flat connection by just saying that the L-1 is a translation operator, so this is natural flat connection. So the step 2 is, so the step 1 was to form the infinite rank VOA bundle, and the step 2 is to form what is called out action. So for that, I take the n distinct point from the Riemann surface, and the out Lie algebra is this. So this is the Lie algebra consisting of a global section or certain sheaf. So the sheaf looks like this. The V is the vector VOA bundle that I have constructed before, and one is the one from sheaf, and I modulo out some the image of the connection. And the reason why I wanted to incorporate the local coordinate into V is because somehow I want to write down this formula. So this makes geometric sense. And otherwise, every time you fix the local coordinate, I can trivialize V with abstract vertex operator algebra. But this way I can just write down the global coordinate independent description. And I say this is the Lie algebra. This is because what is inside is a sheaf of Lie algebras, and why it is a sheaf of Lie algebra is because this Lie algebra structure comes from the structure of the vertex operator algebra. So this way I can transfer the structure of the VOA into this geometric setting by incorporating the local coordinates. I hope that answers your question. Okay. So I take the modules, and here's another thing I have to do. So I choose a local coordinate at each point, and then this out V algebra acts on the tensor product of the modules by this formula. And there are a couple of things going on here. One thing is that, so there is a sum over the points, so it's kind of coproduct action, which is quite natural. The other thing is that, so mu is taken from here, which is a global section of this sheaf. So any element is a kind of, it looks like V tensor one form, but in order to see it as a V tensor one form, you have to choose a local coordinate. So you do that first. I don't know, the order doesn't matter. So mu ti is mu. So this is a section, and I do two things. I expand it at the point xi, and I trivialize the result by ti. So only after locally trivializing by ti, I can apply the module map, because otherwise, so the module map is defined from the VOA side. So I have to identify mu with something in V by local trivialization, and then I can apply this. And the other thing is that mu t is a kind of one form, so I can I can do the counter integral, which is residue, and then I get something well defined, and I apply it to the mth component of this tensor product. And this is an action of the Lie algebra, out Lie algebra. And the final step is to take the invariant part of that Lie algebra. So I take the tensor product of them on which the out Lie algebra is acting. So I define the invariant functional over the tensor product of M1 through Mn in terms of this Lie algebra. And this, for me, so this is the space of functionals on the tensor product of the modules satisfying the word identities. And word identities, for me, the word identity is not really about the stress energy tensor, but everything that comes from the vertex operator algebra. And in the first lecture, the word identity was like the stress energy tensor is a global field. Instead of saying that the stress energy tensor is global, I define the conformal block so that the stress energy tensor is actually global. So does it make sense? In the first lecture, it was said that the stress energy tensor is so that because the conformal blocks has been given, and the word identity is that the tensor stress energy tensor is globally meromorphic, and I do the same thing in different order. I define the space of conformal blocks so that the stress energy tensor is globally meromorphic. And there's also the fact that if I vary these surface and points and local coordinates, these spaces of conformal blocks are fibered over the big moduli space. And this this bundle is equipped with a projectively flat connection. Okay. So actually, I had time to compare this construction to the first lecture. So very often times, the module that we have chosen has a highest weight vector of alpha I. So I take the highest weight vector W alpha I. And it is also often the case that those points are located in the same local chart. So if I choose some local chart, and the T is the local coordinate on the chart, I choose this coordinate induces a local coordinate at each point by just saying T minus T aside, and I also call the coordinate of xi zeta I. So I take a conformal block out of this the space of conformal blocks, and often people write that the result of evaluating the conformal blocks on the tensor product of the highest weight vectors as the bracket or the vertex operators. Right. And also there were bootstrap axioms and the linearity. So now I have given the definition of the conformal blocks. Those axioms are what we have to check. The linearity is obvious because it's a linear functional. I mean, given that I understood correctly. The symmetry comes from the flat connection because of the flat connection, you might be able to exchange the values, the variables. The closing symmetry, I think it is closely related to the factorization that I will see later. And I think this is the both level creature. One identity I have already mentioned. The locality is kind of built in the axioms of the VOA. Okay, so now that we know the definition of the conformal blocks, let's go to this, how the tensor structure comes from the conformal blocks. And I think that studying the tensor category of VOA modules is more or less the same thing as studying the conformal field theory on the sphere, T1. So T1 is covered by two complex planes, and this is special case because we can choose a global coordinate T on the neighborhood of 0, and I just choose the 1 over T on the other side. So again, I take modules of the VOA, and I take n points on the complex number, complex plane. So this is supposed to be C0. then I can form this functor from the category of modules over V to the vector space that assigns. So these m's are given later. This is variable. So if you insert the module here, you get stable conformals, which is a vector space. And I didn't mention the conjugate. This is the kind of dual. This way I can make this functor called covariant. For the VOA case, it's actually safer to pick some subcategory of V modules, and the assumption is that it at least contains the vertex operator algebra itself, because it will play the role of the unit. Okay, so this is the definition of the tensor product of modules, which comes from the Juan Lebowski-John, and this kind of, yeah, okay, so this paper has a little bit different approach than what I'm presenting, so this is my interpretation, kind of. But if this definition is wrong, it means that just I'm wrong. So I take the two modules, M1 and M2, and take Z from the complex plane. I have to assume that this Z is not zero, and what is called the tensor, PZ tensor product of these two modules is the representing object of this functor, where M1 is inserted in at Z and M2 is inserted at 0, and the module inserted at infinity is the variable of the functor. So more precise, more concretely, we always have canonical or natural isomorphism between the result space of conformal blocks and the space of homomorphisms between the tensor product to n. So in our case, our category will be semi-simple, so we can just assume that C is a semi-simple, and this result might be also useful for other semi-simple categories. The assumption is that, so it might be the case that the simple objects are labeled by finite sets, so I might be a finite set, but I don't have to assume that. Instead, I will assume that if I fix M1 and M2, then there are finally many possibilities that the space of conformal blocks might be non-zero. If this is true, then the tensor product of M1 and M2 is just a direct sum of the simple object, and the coefficient is the space of conformal blocks. This is very natural. You can just run over all simple object, and this space of conformal blocks capture all possibilities of whatever happens. In terms of the unit law that it must be satisfied by the tensor product, there is very general result about the space of conformal blocks, which is the propagation of vacua, which is that if you insert the vertex operator algebra itself here, it doesn't matter. You can just remove the V itself out of the space of conformal blocks, and then you end up with the space of conformal blocks with 1 point less. This map is very canonical because you can just evaluate this conformal block by the vacuum, and this is analogous to the case of R modules where the multilinear map is determined by the value at the unit. And in particular, this gives you the unit law, so the V tensor M and M tensor V is canonical isomorphic to M. The associativity is more subtle. It might or might not be true, but let's assume that C is semi-simple and assume the same conditions as above, as before. What we want for associativity is really the ability to glue two of them to a tensor product. And this might or might not be true, but if this is true, we know the formula for the tensor product inside, and by the linearity of, so this is also factorial in other variables, so by the factoriality of the conformal space, conformal blocks, I can just pull out the coefficient out. Then the end result is the sum over all simple representations, and there's a simple representation of the dual of the simple mode object, and here's a pair of that. And so I put the question mark over here, so this might or might not be true, but if this is true, the first quantity and the last quantity equality between them is called the factorization, because you can compute the space of 4-point functions out of pair of 3-point functions. And this will be, if this happens, there is a good hope to have associativity of our tensor category. And we can call it a tensor category given that there is associativity. So here's a summary of the tensor structure. I'm just saying that there are there are a lot of there is similarity between the R module and the BOA modules. So so in terms of the definition, I just replaced the space of multilinear maps with space of conformal blocks, and there are analogous structures that are expected for space of conformal blocks. There are also differences. One big difference is that it's much harder to show the existence of the PC tensor product of the BOA module. And another difference is that actually you can choose different tensor product structure for different Z, but these different PC tensor products are connected by a parallel transport, and this parallel transport comes from the local, the projectively wrapped connections. When you fiber the space for conformal blocks of the moduli space, but if you want to get just one monoidal structure, you just use the tensor product at 1. Okay, so the result was, what was our result? Well, our result was about the categorical equivalence between the represent modules of the quantum group and the modules of the vertex operator algebra under this parameter matching. And the idea is just this is more like how else I should do if I don't have any fancy gadget for category theory. I just want to compare the home spaces. On the one hand, on the quantum group side, I have these home spaces, and on the BOA side, I have the space of conformal blocks. So I just want to compare these two spaces. There are a couple preliminaries coming from the twisted homology stuff. So I take the T again, which is irrational, and I take Z, which will be the variable of the conformal block, and I just assume that these complex numbers are distinct. And then I also take these non-negative integers, and given Z, I write YZ of M, which is the space of integrated variables. There are M variables, and I assume that they are distinct, and it doesn't touch any of the ZI. So if I fix the Z, I write the local system L on the YZM. That is associated with the multi-valued function of this formula. And I think this result is usually attributed to Varchenko. I take the Balmer module of the UQSL2 of the highest weight q to the power of r-1, and under this parameter matching, there is this isomorphism of the vector spaces. On the left-hand side is the space of singular vectors. So it is annihilated by E, and I capture the subspace that has exactly the highest weight q to the r infinity minus 1, and there is isomorphism between the space of singular vectors and the twisted homology in terms of the local system. And just in case, just in case you wonder what the twisted homology, it is the space. It consists of cycles on which you can do integration by parts. That's it. But just by looking at these two spaces, there is no parameter matching. The parameter matching happens in exactly the same way, but how to see this parameter matching, I think the easiest way to see the parameter matching is to consider the R matrix braiding on the left-hand side, and there is also way to exchange variables by the Gauss-Manning connection, meaning that I can fiber this homology group over the configuration space, and there is a natural connection on that bundle. And if you compare these two braidings, they coincide under this parameter matching. Okay, so there is what we call quantum group method. It consists of two steps. The first step is okay. Now that we know that there's isomorphism between scalar vectors and twisted homology, so I just integrate the function that I have written down as psi, and I integrate that function over the cycle taken from here. But of course, we know that isomorphism, so you can say that C is actually a singular vector in the representation. And so Kalle and Evelina did so this is my interpretation of what Kalle and Evelina did. So first of all, even though this is the tensor product of our modules, actually it factors through the tensor product of irreducible representations. So this map factors through this space, and this space of singular vectors is of course isomorphic to canonically isomorphic to the space the homomorphism home space of our category. Another thing is that so this is the second is most important. I mean, third is of course important. The second thing is that every time you take a singular vector, the result satisfies Möbius covariance and the BP's equations. And lastly, if I take a vector from a certain channel of this tensor product located at ith and I plus first location, and if I restrict, I take the vector out of there, the results exhibit a particular asymptotic behavior when zi plus 1 approaches the I. And so this is the integral representation of the solution of the BPZ equation, and this comes from the Dutton-Fatiev construction of the conformal block. So this df stands for Dutton-Fatiev. And my contribution is, in some sense, no more than extending or interpreting their results in terms of the conformal blocks. And you get the solution of the BP's equation and the Möbius covariance and the asymptotics. So there is a way to extend the result to a conformal block, and if you restrict to the certain channel on the left-hand side to then so if you restrict to the certain channel of the tensor product between I and I plus first component, then you get the result landing in this tensor product of 3-point conformal blocks and the rest. So so actually there are a couple of non-trivial statements happening here. First of all, how to understand the tensor product of two space of conformal blocks as a subspace of this. This comes from the trace, taking a trace over Ls prime and Ls happening here. So because it takes a trace, it involves infinite sum. So there is a issue of convergence, and this is often refers to as a convergence of conformal blocks. And in our case, we are good because we have differential operators, the differential equations, so we can control the convergence by the differential operator. Well, in some sense, this is just an extension of Pertola, but I think extending a function to a conformal block is a little bit non-trivial, because if you try to do that, there's always a problem of well-definedness, and showing that it is actually well-defined is a little bit of work. It's also worthwhile to extend to the conformal blocks, because so the definition of a tensor product relies on the space of conformal blocks, so we really need to functoriality of the space of conformal blocks in terms of the modules. So yeah. But anyway, now that we know that there is a relation between the space of singular vectors and the space of conformal blocks, we can leverage this map to compare the module category of quantum group and the module category of the VOA categories, VOA module categories as tensor categories. And yeah, so I don't go to the detail of that, but yeah, I think that's all what I want to say.
So any question, remarks, comments? Yes.
So this relation between categories, so you also respect the braiding.
Yeah.
So you have R matrices coming from two sides which coincide.
Yeah. So the braiding is also match. Yeah. I can just check that these two braidings match, and it's very natural because on the I don't know how to say the left-hand side, there's the matching of the braiding also already manifest already at the level of the implicit homology, and yeah, I don't know. Sorry, the proof is just by computation.
But my question is the following. So from quantum group side, so you can produce knot invariants out of the matrices. So in this context, they call Jones polynomials.
Yeah.
And does your relation between two categories allow to get some insight of on geometric nature of color Jones polynomials?
I don't know.
So the knot invariance, you only get the parameters root of unity, or can you get it in the generic case? Because this is generic.
Yeah, but it doesn't matter, even at roots of unity, if you can get some geometric interpretation of from your view of matrices. Do you see maybe potential
Application to the knot theory.
this as application?
I never thought about that. Sorry.
Maybe we can discuss.
Yeah.
Okay.
Any more questions? Raphael?
So, sometimes the relationship between the Tsenko-Faddeev integrals and the quantum groups have to do with the Verlinde operators. Do they appear somewhere in your story?
They might have appeared, but I haven't aware of that. Yeah.
And from the probability point of view, I mean, the generalization that you did, how does it affect in the probability side? Because there's a relation of this PQZ that we had in now here.
Yeah, I think the original motivation of Kalle and Pelto was to construct a creation function for a partition function of SLE of quantum group in a very explicit way. I mean, in some sense, so I mentioned other results of this of the same flavor, but they, yeah, I mean, they don't really give the explicit construction of the conformal blocks or correlation functions. And the benefit of doing that is we really have the correlation functions of the products of correlation functions.
Okay, so the probability side is the same thing. But
Yeah, I assume the probability theory. In the probability theory, you really need to know what are those functions in a way. That might be a benefit.
More questions? question so we can thank the speaker again. And I think there is a
very nice to be a week with discussion with colleagues about the lecture. If there are some open questions that come into your mind.